I greet you in the love and the light of the infinite Creator. Event is coming soon. YouTube channel. Here's the latest intel.
The next Big Bang human consciousness in the universe's ultimate secret. For at least 200 years science has been telling us that any ideas of spirituality we might hold dear are little more than ignorant leftovers of a superstitious past, foolish relics. But the truth is, physics itself, that most foundational of all sciences, has now progressed far beyond that initial, dismissive assessment, to a conceptual worldview far more accepting of spirituality than ever before. To grasp the nuts and bolts of this new science, then, is to understand the nuts and bolts that support a new, evolving and far more sophisticated grasp of spirit than has ever before been available to us. This new conceptual framework is absolutely critical to our grasp of spirit, and, frankly, for those previously unfamiliar with the discoveries of modern physics, this new framework may at first seem nothing short of otherworldly itself. As the old saying goes, the truth can at times be far stranger than fiction. So let's start by taking a close look at what the new physics has to tell us. In 1964 the scientific world was literally turned on its head by a new theorem, but very few at the time understood just what had taken place. Indeed, so astounding were the material, philosophical, and spiritual implications of this assertion that it would soon be referred to as the most profound discovery in science. One yet even today, few beyond a small community of physicists have come to grips with its meaning. The conceptual implications for particle physics were so extreme that for decades after its announcement many within the scientific community resisted its implications, as do some resist them to this day. The theoretical contentions offered in 1964 have been confirmed and replicated in laboratories across the globe on numerous occasions, and today there is no question that the original assertion was correct. This monumental insight is called Bell's theorem, and the sea change it caused in physics is still being digested as I write. So central is Bell's theorem to our understanding of the physical universe, how it functions, and what that means for us as human beings, that to grasp its implications is crucial for anyone interested in the science that today enables us to envision universal processes as far more than simply material phenomena. Yet, simultaneously, to truly grasp the new reality Bell's theorem implies, it is essential that we first understand the old reality it so violently overturned. Today many within the scientific community believe that our modern science, that is, the science of observation and testing, of the scientific method, was inaugurated in the 17th century when Galileo Galilei first pointed his homemade telescope toward the heavens and started poking around. How did this new science differ from previous approaches to the study of physical phenomena? Dr. Dean Radin, laboratory director at the Institute of Noetic Sciences in Petaluma, California explains. Classical physics began in the 17th century when pioneers such as Italian mathematician Galileo Galilei, French philosopher René Descartes, German astronomer Johannes Kepler, and English mathematician, and alchemist, Isaac Newton advanced a new idea. The idea was that through experiments one could learn about nature, and with mathematics, describe and predict it. Thus rational empiricism was born. Classical physics was extended and substantially refined in the 19th and 20th centuries by luminaries like James Clerk Maxwell, Albert Einstein, and hundreds of other scientists. 2. This physics, called classical, or Newtonian, or material physics, has made an enormous contribution to our understanding of the universe we inhabit, and as a result has had a profoundly positive effect upon the overall human condition. Food production, health services, economics, education, transportation, etc., have all been vastly improved as a result of scientific applications made available through analysis and testing. No doubt, material science has been a boon to humankind. Initially, this new science looked outward as had Galileo toward the planets and stars for answers regarding how the universe worked and the matter by which it was constructed. Larger and better telescopes were developed in order to augment this process, and today, of course, Spacecraft have been constructed that fly to points distant enough to inspect and photograph distant terrestrial bodies. As a result, a great deal has been learned. In the 18th and 19th centuries, enormous strides were made in terms of our understanding, not only of the greater cosmos, but also of the physics by which it functions. Most of the planets, their orbits, and their relationship with the Sun were established early on. The mathematical calculations for all of this fit nicely within the prevailing understanding, or model, of the universe, and all of these findings both confirmed and augmented our grasp of Newtonian physics. The emergence of quantum physics. Still, despite all the advances, there were some oddities that did not quite fit. In 1801, for instance, British physicist Thomas Young conducted a double-slit experiment in an attempt to deduce the true nature of light. Prior to that, it was assumed that light was composed of small particles of matter, but the result of Young's experiment seemed clearly to indicate that light was in fact a wave. It was presumed, as a consequence, that light waves would require some sort of medium in order to propagate, conceptualized as a luminiferous ether or ether wind, and the search for this medium was promptly initiated. Physics soldiered on essentially unruffled by all of this, however, still confident in its overall grasp of the universe. But this subtle medium, despite numerous attempts at detection, remained elusive. As a result, light continued to be a thorn in the side of Newtonian physics, thus it was naturally toward the study of light that much attention became focused. In 1900, for instance, American physicist Max Planck developed a mathematical model that demonstrated that light appeared to exist as distinct bursts or packets of matter. Planck named these packets quanta after the Latin quantas, which translates as essentially how much. Planck's discovery proved the birth of what we today call quantum physics, that is, the study of that group of infinitely small particles that ultimately comprise all matter. Then, in 1905, Albert Einstein, an unknown physicist at the time working as a patent clerk in Switzerland, clearly demonstrated the validity of Planck's quanta, but it was a proof that also allowed that light had to have both wave and particle characteristics, a perplexing side issue. Quantum understanding snowballed rapidly. Dean Radin tells us that, Danish physicist Niels Bohr showed how the quantum concept could explain the structure of the atom, 1922 Nobel Prize. In 1924, Louis de Broglie proposed that matter also has wave-like properties, 1929 Nobel Prize. In 1926, Erwin Schrödinger developed a wave equation formulation of quantum theory, 1933 Nobel Prize. Our insight into quantum mechanics was accelerating rapidly, but, despite all of the progress, the seemingly dual nature of light remained a vexing problem. Was light comprised of particles or waves? No one could say. The Big Bang Theory. Meanwhile, additional progress was being made at the observatory by looking in the opposite direction, far out into the depths of the universe. In 1929, as an example, by carefully analyzing the redshifts, observed light frequencies, of distant galaxies, American astronomer Edwin Hubble demonstrated that the universe was expanding. An expanding universe was evidence contrary to the steady-state theory of the universe, or a universe that was essentially constant and eternal. Hubble's finding also suggested that our universe, since it was now seemed to be expanding, may naturally have had a beginning, that is, a moment when all that matter had been consolidated in a single point before it started to expand. Over time this beginning became conceptualized as what we today call the Big Bang theory of the universe, or a moment when the material universe emerged from a background of utter nothingness in an enormous burst of heat, light, and matter. The name actually came from British astronomer Fred Hoyle, who quipped one day on British radio that the theory sounded like little more than a Big Bang, and while this was stated in jest, the term stuck, nevertheless. The Big Bang theory postulates that the universe emerged from a singularity, a point of infinite density, which remains, frankly, beyond our current physics to explain, or, as humorist Terry Pratchett once quipped, in the beginning there was nothing, which exploded, some 13.8 billion years ago as an incredibly small and incredibly hot point of matter. According to the theory, this material then inflated, expanded then cooled over time, allowing for the formation of light elements like hydrogen and helium. Due to a slightly uneven distribution of matter throughout the universe, gravitational attraction then began to consolidate these elements into clouds, which over eons formed the stars, planets and galaxies that comprise the celestial panorama we observe today in our nighttime sky. Evidence supporting the Big Bang theory of creation then began to accumulate. This evidence included the original redshift Hubble discovered, the discovery of cosmic microwave background radiation, which had been predicted as a residual product from the heat of the initial inflation, and more recent redshift observations of distant supernovae indicating that the expansion of the universe is actually accelerating, and which suggest the existence of dark matter in substantial quantities as the driving force behind this acceleration. This explanation of the Big Bang is, to say the least, a very brief and general summary of a vast and complex event, but it serves our purposes by bringing us forward conceptually to the year 1964, and the model of the universe that was prevalent at the time Bell's theorem made its shocking appearance, minus the dark matter, which was theorized later. The truth of the matter is, however, while the Big Bang theory provided the universe with both a beginning and a direction, it did not alter the assumption that the universe was fundamentally a material phenomena, a belief central to modern science ever since Galileo had peered through his telescope. History tells us, as an example, that when asked by Napoleon Bonaparte in the early years of the 19th century as to why his most recent treatise did not mention the existence of God, the great French scientist Pierre-Simon Laplace was said to have remarked, "I had no need of that hypothesis." Later, and likewise, Laplace explained to an admiring audience that, we may regard the present state of the universe as the affect of its past, and the cause of the future. In other words, Laplace, along with almost all other scientists at the time, believed that the universe was little more than a vast, material machine, driven by physical forces, and nothing more. If, for instance, you could determine the position and direction of every particle in the universe at any given point in time, it would be possible, at least theoretically, to crank that picture forward or backward, observing as you did every event that had taken place in the past while accurately predicting every event that would take place in the future. This view therefore supported the notion of a deterministic universe, and a universe that was devoid of either free will or human consciousness as a result. Importantly, this understanding, or model, of the universe rested on certain suppositions that were accepted as true and universal by material physics down through the years simply because the universe appeared to function in accordance with them. The Big Bang was conceptualized as the beginning of an entirely material process that had evolved over eons in accordance with the known parameters of Newtonian, or classical, reductionist, or material physics. In that sense, the universe was still perceived essentially as a vast, physical mechanism, a machine that was now understood to be a bit more complex than it had been conceived during the earlier days of, say, Pierre-Simon Laplace 150 years before, but differing now only in terms of its sophistication, not its fundamental nature. Thus Laplace's statements regarding the absence of God and the predictive power of the original conditions still held true as far as modern physics was concerned. The universe was also considered to be a true, functioning reality, and a reality that, having been put in motion by a natural, although inexplicable, occurrence, remained utterly deterministic, events formed and driven forward in time, no longer by the unseen hand of God, but by random particle collisions alone. All events occurred due only to the action of physical forces in contact or proximity with one another, and no force, field, or matter could, according to Einstein's calculations, ever travel faster than the speed of light. But the wave-particle nature of light still remained an intellectual conundrum that, much like one rotten apple, threatened to subvert the entire structure of physics if not sensibly accounted for. Uncertainty principle neuters Newtonian physics. Still, as far as the quantum theory was concerned, great new strides were being made. Physicist Nick Herbert tells us, for instance, that, by the late 1920s physicists had constructed a quantum theory adequate to their needs. They possessed, thanks to the work of Heisenberg, Schrödinger, and Dirac, rough mathematical tools that organize their quantum facts to a remarkably accurate degree. At this point Hungarian-born world-class mathematician John von Neumann entered the picture. Von Neumann put physicists' crude theory into more rigorous form, settling quantum theory into an elegant mathematical home called Hilbert space, where it resides to this day, and awarded the mathematician's seal of approval to the physicists' brand new theory of matter. 4. But the enigma of light continued to plague quantum theory, and it is precisely here where the old physics of determinism and cause and effect began to unravel. In 1927, for instance, German physicist Werner Heisenberg authored his now famous uncertainty principle, the intellectual consequences of which did great mischief to Newtonian physics. Heisenberg was at the time attempting to measure the precise speed and position of a particle in order to predict its future position, a process that should have been entirely within the accepted parameters of Newtonian physics. But Heisenberg discovered that this could not be done. British physicist Stephen Hawking tells us that Heisenberg's uncertainty principle indicated unequivocally that the more accurately you try to measure the position of the particle, the less accurately you can measure its speed, and vice versa. This finding sent shockwaves rippling through physics. Moreover, Hawking tells us, this limit does not depend on the way in which one tries to measure the position or velocity of the particle, or on the type of particle. Heisenberg's uncertainty principle is a fundamental, inescapable property of the world. 5. In a very real sense, Heisenberg's principle delivered a body blow to Newtonian physics. Because, if the precise state of the universe was impossible to measure at any given moment, then any state either before or after was also impossible to calculate. It was as simple as that. Laplace had been wrong. Determinism, material cause and effect, even the forward-moving arrow of time surely appeared to be on the ropes. Suddenly, many of the underlying presumptions upon which classical physics rested had seemingly evaporated into thin air due to Heisenberg's principle. What was going to replace them? Moreover, what did Heisenberg's findings actually mean? How could it be that aspects of the material universe were, had always been, and would always be, utterly beyond our ability to measure? And there was still more damage as a result of Heisenberg's new principle. Because, if particles could not be clearly defined in terms of their position and movement, then particles could no longer be clearly defined as material objects anymore. If, after all, the position and movement of a particle could not be described with precision, then in a sense a particle could only be described with imprecision, a mathematical approximation. A photon, for instance, could no longer be considered a discrete particle, but rather a combination, part particle, part wave, or a mathematical description now called a wave function. Even more importantly, if the manner by which a particle was measured, or observed, altered the resultant observation, a fact Heisenberg had demonstrated, then it followed logically that observation itself had to be a fundamental aspect of reality. Physics had been thrown for a loop. A world of pure possibility. Magic. Indeed, some physicists, Heisenberg included, began to interpret the wave part of the particle, wave aspect of light as meaning that particles became particles only when observed, and remained waves, that is, in a state of material potential, when not observed. This, of course, was an extraordinary claim, something that many physicists thought sounded disturbingly akin to ancient superstition, like magic or voodoo. What Heisenberg and his colleagues were suggesting, in essence, was that the unseen world of quantum mechanics was not a material realm at all, but a realm rather of pure potential. That's right, quantum researchers like Heisenberg argued that the fountainhead of the physical universe appeared to be utterly immaterial. And as damaging as all of this was to classical physics, even more shocking news was on the way. Because if the foundation of our physical reality arose from a source of pure potential, was not material at all, then what, exactly, was this non-physical stuff? Could it even be called stuff? At this point in time many scientists became dizzy just trying to get a handle on the facts, and who could blame them? Nick Herbert explains the next leap in logic that took place. If we take quantum theory seriously, it seems to demand that the world before an observation is made up of pure possibility. But if everything around us is only possible not actual, then out of what solid stuff do we construct the device that will make our first observation? Either there are some physical systems whose operations unaccountably evade the quantum rules, or there are non-physical systems not made of multi-valued possibility, but of single-valued actuality, systems that exist in definite states capable of interacting in an observational capacity on indefinite quantum-style matter. Yet it was clear that all material systems consisted of particles, and that these particles always obeyed the rules of quantum mechanics, not individually, but in statistical aggregates, because these rules had been tested and verified throughout countless experiments. On the other hand, Herbert continues, we are aware of at least one non-physical system that not only can make observations but actually does so as part of its function in the world, the psychological system we call human consciousness. 6. This assertion, while sound mathematically and entirely logical, was so startling that it literally turned classical physics on its head. A science that had accepted as utterly valid a universe constructed of, and driven by, material particle movement was told suddenly that it had it all wrong from the very beginning. And make no mistake about it, that's exactly what was being said. The general idea of von Neumann and his followers, Herbert explains, is that the material world by itself is hardly material, consisting of nothing but relentlessly unrealized vibratory possibilities. From outside this purely possible world, mind steps in to render some of these possibilities actual and to confer on the resultant phenomenal world those properties of solidity, single-valuedness, and dependability traditionally associated with matter. This kind of general explanation may be enough for philosophers, but physicists want more. They want to know exactly how it all works, in every detail. 7. Indeed, the notion that our material reality was not real after all was simply too much for many physicists, and their response at the time was entirely reasonable. No determinism, cause and effect, or arrow of time? What was happening to the foundational principles of classical physics? Many physicists tossed up their hands in dismay, others in disgust. One of those physicists was the extraordinary Albert Einstein himself, the very father of relativity theory, and the most respected physicist in the world. All of this sounded crazy to Einstein. As to the notion that the universe was the construct of little more than the capricious whims of human observation, he supposedly responded with the now famous quote that, God does not play dice with the universe. Obviously, he did not agree with the newest speculations of quantum physics. Einstein bristled at these new interpretations of quantum theory to the point that in 1935 he, along with Boris Podolsky and Nathan Rosen, issued a thought-provoking analysis now known as the EPR, Einstein, Podolsky, Rosen, paper. This analysis was meant to be a clear-headed challenge to the wave-function description of matter that had been adopted by many quantum physicists, and described above. The EPR paper insisted that the position and momentum of any given particle had to be able to be measured far more accurately than Heisenberg's principle allowed for, or else information between certain entangled particles. Erwin Schrödinger had previously demonstrated that when quantum systems interact their wave functions become entangled, and they will remain entangled even when no longer interacting, would be theoretically transferred faster than the speed of light, instantaneously in fact, which was a fundamental violation of Einstein's theory of relativity. According to the EPR paper, hybrid particles like wave functions, and instantaneous transmissions, what Einstein called spooky action at a distance, were inelegant solutions clearly out of line with relativity theory, which was the accepted gospel of physics at the time. In that sense, then, the EPR paper was issued as a direct challenge to quantum theory as it was currently being developed. Bell's theorem and a non-local universe. This was more or less the state of affairs in 1964 when John Stuart Bell entered the picture. Without going into great detail, suffice it to say that Bell demonstrated in his theorem that the EPR analysis was right, but that its conclusions were wrong, and that supraluminal, faster than light, entanglements were not only possible, but required if quantum theory was to make sense. Prior to this, physics had always assumed the universe to be local in nature, that is, Interactions between physical systems had of necessity to involve a signal transferred by force at a rate below the speed of light. Bell's theorem, on the other hand, demonstrated that the universe was in fact non-local. A non-local effect is an interaction that does not involve force, nor does it involve the transfer of signals, and it happens instantaneously regardless of the distance between objects. 8. And as a consequence the spooky action at a distance Einstein had argued against, was, in fact, a foundational aspect of the universe. Not only that, but within a few years, and repeatedly, Bell's theorem was tested in the laboratory, and found to be accurate. The science was now clear: we live in a universe that is non-local. As Columbia University physicist, Brian Greene, noted, this is an earth-shattering result. This is the kind of result that should take your breath away. 9. The fact is, this finding has taken a good many people's breath away. And if all of this is not weird enough for you, Philippe Eberhardt, then working at Berkeley, soon demonstrated that no quantum calculation will ever result in an observable superluminal connection between the patterns of individual quantum events. 10. Non-local interactions are thus built into the fabric of the universe, but in such a way that we can never actually observe them. But that does not mean we cannot observe their effects. For as Herbert explains, the present situation seems to be as follows: quantum theory is supraluminal, faster than the speed of light; quantum reality is supraluminal, but quantum appearances are not. Since quantum theories of consciousness assume that the cause of individual quantum events lies in the mental world, and Bell's theorem proves that the causes of some quantum events must be supraluminally connected, then we should expect to find some mental events that behave like the Bell connection, that is, human experiences that are unmediated, unmitigated, etc. 11. In the span of approximately 75 years the world of particle physics had been turned upside down, and the philosophical and spiritual implications of this have yet to be fully digested by either science or the public in general. Indeed, the implications are mind-boggling. Our conceptual understanding of the universe, of which we are all material manifestations, changed from one that might be characterized as a vast, relentless, grinding particle machine, to one that seems almost, well, magical. What other word will do? As physicist Richard Feynman noted, what I am going to tell you about is what we teach our physics students in the 3rd or 4th year of graduate school. It is my task to convince you not to turn away because you don't understand it. You see, my physics students don't understand it. That is because I don't understand it. Nobody does. 12. Yet to this day many scientists continue to scoff at any understanding of physics beyond the material boundaries of the classical interpretation, as if all the advancements in quantum theory had never really taken place. We are often lectured that any sort of spiritual or religious belief we may hold are the products of faith alone, discredited convictions rooted in either medieval dogma or rank superstition, that they are simply not scientific. But today the truth of the matter is actually the polar opposite, for it has been clearly demonstrated that those individuals making these charges are the ones trafficking in faith, in fact clinging to material dogmas that physics has left behind in the dust. Laplace's material cosmos is now an intellectual relic of the past, overturned, not by faith, but by science. All is one in the entangled universe. It seems to me, for a moment, then, that the seemingly limitless world of the observatory and the minute world of quantum mechanics are far more than even light years apart, that this universe of colossal, spinning galaxies, numbered now to be in the hundreds of billions, and the world of the particle wave function are so intellectually incompatible that today they seem almost alien to one another. Then again, maybe they are not. For if the Big Bang began with a singularity, as we are told, and a singularity that was infinitely dense, then every particle that has ever emerged was initially contained within this extraordinary particle of infinite density, merged or forged or crushed in some magical way into this one tiny something. The seeds of our entire universe were fused into that one, and if all were once one, then is it not reasonable to speculate that all were entangled at that moment, if indeed it can even be described as a moment, and thus quite possibly remain entangled to this day? Suddenly, then, from this perspective, the universe no longer appears to be an alien landscape of far distant, whirling bodies at all, but rather a vast masterpiece of infinite and instantaneous communication, of instant knowing. As Feynman suggests, what, precisely, the world of quantum mechanics might ultimately be determined to be remains a mystery, and may well remain a mystery some time to come, but what has already been established is surely enough to reformulate our ideas about what the universe is and how it functions. For, while quantum interactions cannot be observed, their effects can nonetheless be experienced, and those experiences can be demonstrated scientifically. But for now the most important concept for us all to hold on to is that of a vast and connected universe of instantaneous communication and knowing, of a universe that begins to look far more like a conscious organism than it does a grinding material mechanism, and this is far more than mere layman's interpretation. Indeed, it was the great British physicist Sir James Jeans who penned the quote heading this article, "The stream of human knowledge is heading toward a non-physical reality. The universe begins to look more like a great thought than a great machine." This a view of reality shared today by many physicists. In all probability we will not have all the answers to the true nature of the universe in our lifetimes, but one thing does seem abundantly clear: the old dogmas of material science have been proven relics of the past, and a new concept of a foundationally conscious universe appears clearly to be arising to take its place. And there, in simple terms, rests the case for human consciousness, for our compassion, and the spirit that binds us all.
Please like us and share with your social media. Please subscribe and click the bell to be notified of our new videos.
Remember to check out our playlist for important intel you may have missed.
Be sure to enter our subscriber appreciation $100 monthly giveaway. The link is in our description.
And visit our sister channel. The event is coming soon for additional intel and information.
Stay tuned.
Victory of the Light.
Event is coming soon. YouTube channel.